Hello students, in this video lecture I am going to discuss the concept of upper bound, least upper bound and join in a partially ordered set. So the first question which arises is, what do we mean by upper bound of a subset of a PO set? So for this, let us take a PO set P less than equal to and let S be a subset of P. Then an element X belonging to P is called an upper bound of the set S if every member of S is less than equal to X. If this happens, then X is said to be an upper bound of the set S. And diagrammatically, if we try to analyze this situation, because X is an upper bound, so X is on the right and every element of the set S is on the left. So in the hash diagram, X will be at the top and every element of the set S will be at a lower level than X, because every element of the set S is on the left and X is on the right. So the element which is on the right will be at the top, so X will be at the top, and every element of the set S will be at a level lower than X in the hash diagram. Then coming to a note which gives a notation of the set of all upper bounds of the set S. If we take the set of all upper bounds of the subset S of P, then the set of all upper bounds of the subset S of P is denoted by S U, where U is this subscript, and this particular notation stands for that this is the set of or collection of all upper bounds of the set S. Now coming to the second concept, which is the concept of the least upper bound of a subset of a PO set. Again, let us suppose that P less than equal to is a PO set and S contained in P is a subset of P. Then an element X belonging to P is called least upper bound, or it is called the supremum of S, or it is denoted by sup of S if the following two conditions are satisfied. Now X will be least upper bound. In short, we can write it as LUB, which means least upper bound, if the two conditions are like this, that X must be an upper bound and X must be least of all upper bounds. That is, if there is any other upper bound of S, then X must be smaller than that, or X must be lesser than that. So these are the two conditions. If X belonging to P has to be if X is to be the supremum of S, or it has to be the least upper bound of S, then as I just mentioned, the two conditions are that X should be an upper bound and it should be least of all upper bounds. So this is what is written in the first condition, that X should be an upper bound of S, which means that every element of S should be smaller than X, or S is less than equal to X. And the second condition that must happen is that X must be least of all upper bounds of S. If there is any other upper bound of S, which means if there is any Y belonging to SU is the set of all upper bounds of S. If there is any other upper bound of S, or if there is any Y belonging to SU, then X must be less than equal to Y. So X must be lesser than Y. So if these two conditions are satisfied, then we say that this X is the supremum of the set S, or it is the least upper bound of S. And then again there are a few notes which give notation which is quite common when we are talking of the least upper bound or supremum of a subset. So if we are in a PO set P less than equal to, and if we pick up any two elements A and B belonging to P, then if we talk of the supremum of A and B, or the least upper bound of A and B, so this means that the subset S which I am taking in this case is to be the set consisting of two elements A and B. Because A and B are members of P, so this S is very much a subset of P, and you are talking of supremum of S, or you are talking of least upper bound of S. So the supremum of S or least upper bound of S, which is supremum of AB and which is least upper bound of AB, if it exists, it's not necessary that supremum will always exist. If it exists, in that case this supremum or this least upper bound is called the join of A and B, and the notation that we use for join is A V B or A join B. So in general here S was a set consisting of just two elements A and B, but in general if S is any subset of P, then again we can talk of the supremum of S provided it exists, and in that case the supremum is denoted by this Vs or this is denoted by this is called the join of S or the supremum of S. So this join of S is actually nothing but this is another name for the supremum of S, or this is another name for the least upper bound of S. So these are two notations that we have for supremum or the least upper bound of a subset of a PO set. Now coming to a few examples, if we consider a PO set P which is equal to 3, which is a chain of 3 elements, and let us give names to those 3 elements A, B and C. So this is the diagram of the PO set P, which is the chain of 3 elements. Then if we try to find out supremum of some pair of elements, let's say I take elements A and B. Let me keep the diagram here. And now if you talk of if you take S to be AB, which means that I am considering these two elements, and if we want to find out what is the supremum, whether supremum of S is existing or not, where S is the set consisting of these two elements. So I want to find out what is supremum of A and B. Then supremum of A and B is the element which is that element of the PO set P which is greater than equal to both A and B. And from the hash diagram it is very apparent that B is that element which is greater than both A and B together. So here you have A is less than equal to B from the hash diagram, and B is already less than equal to B by reflexivity, because we are in a PO set, and in a PO set reflexivity holds, which means that every element is related to itself. So B is acting like an upper bound for both A and B. Also C is an upper bound for A and B, but out of B and C, which are both upper bounds of A and B, B is smaller than C. So B is the least upper bound. So in that case B becomes the supremum of A and B, because it is the least of all upper bounds. Again, if we take two elements B and C, if these are the two elements that we are taking, B and C, these are the two elements B and C that we take, B and C, and if we try to find out their supremum or the least upper bound, then that element of the PO set P which is greater than equal to both C and B is C, because you have B is less than equal to C and C is already less than equal to C. So C is acting like an upper bound, and there is no other upper bound other than C and B. Other than C for C and B. C is the only upper bound for C and B. So this means that C is the least upper bound for this particular set S is equal to BC. So we have that for when you take S to be the set consisting of A and B, then the least upper bound of A and B is B, which means that in our notation, the notation which we have just given for the supremum, which is the notation of join, then we can say that the join of A and B, because there are two elements in the set S, A and B, so there are two elements only, so we are taking supremum of two elements, which means that we are taking join of two elements. So A join B is B, and in the same way here S consists of two elements B and C. So supremum of S, which is the least upper bound of S, or which is the supremum of B and C, comes out to be C, which means that the join of B and C, which is another name for supremum, that is C. So again, this was these were a few examples of finding out supremum of a subset of a PO set when the PO set consists of just two elements. But if you regard P as a subset of itself, then if I want to find out what is the supremum of P in the, or what is the join of P, whether it exists or not, this means that the join of P should be that element of P such that all the elements of P are lesser than that. Now P consists of these elements A, B and C, and that particular element which is that particular element of the PO set P, such that every element of P is lesser than that particular element is C, because A is also less than equal to C, B is also less than equal to C, and C is also less than equal to C by reflexivity. So C is acting like a upper bound, and this is the only upper bound which P has, because there is no other element, and C happens to be the top element. So C is at the top. So this top element, which is C, is acting like the least upper bound or the join of P. So this is the This basically C is nothing but this is the join of P. Using the notation that we have just done, that supremum can also be written as, can also be called as join, and this is the notation that you use for join. So that was the first example. Now coming to the second example, if you take a PO set to be equal to 4 bar, which is an anti-chain of 4 elements whose hash diagram looks like this. In this anti-chain, no element is related to the other. So all the elements A, B, C, D are non-comparable. They don't bear any relation with the other. Then we want to find out whether the join of A and B is existing or not, which means that the supremum of A and B is existing or not, because we have just randomly picked up A and B, and we want to find out whether supremum of A and B or least upper bound of A and B exists or not. But we find that the supremum of A and B or join of A and B doesn't exist. Why? Because we cannot find any element of P, any element X of P which can act like an upper bound for A and B. There is no element X which is in P which such that X belonging to P is such that A is lower than X also, and B is also lower than X. There is no such element. In fact, these are the only 4 elements that are present in the PO set P, and they are not related to each other. None of them is lower than the other, or none of them is greater than the other. So none of them is a upper bound of any of the any pair of elements. In fact, if you pick up any other pair of elements also, let's say I pick B and C, then again there is no X belonging to P such that B is less than equal to X and C is less than equal to X. There is no common X which can behave like this, which means that there is no X in P which can act as an upper bound, which means that B join C also doesn't exist. So in fact, here this fact that we have written that A join B doesn't exist, this simply means that A and B do not have an upper bound, which means that if you regard S to be a set consisting of 2 elements A and B, then this set S, this set S doesn't have any upper bound, or SU, which is the set of all upper bounds of the set S, this is phi. So SU is phi. So similarly, as I already explained, if you pick up any other pair of elements, not necessarily A and B, but B and C or A and C, they also don't have a join. So in this particular anti-chain of 4 elements, no pair of elements has a join. And in fact, if we try to find out supremum of the whole set, where the whole set P is the set consisting of 4 elements A, B, C, D. So supremum of this whole set doesn't exist, which means that join of P, this doesn't exist, because again for the same reason, you don't have any X belonging to P such that every element of P, every element of this P, every element small p of this capital P is lesser than that. There is no such element X. So because there is no such element, the existence of any such element is not there, which means that there is no element of the PO set P which can act as a upper bound, just because of the simple reason that in an anti-chain no element is related to the other. So there is no question of any relation like this coming, because the elements are not related to each other, and so the set of all upper bounds of P is an empty set, or it is phi. So this was the second example, and now coming to the third example, if we consider a PO set P with the hash diagram given by this, and if we just randomly we have taken a set S is equal to AB, and we try to find out what are the upper bounds of the set S, which consists of 2 elements A and B. So these are the 2 elements A and B, and we can just see that just above A and B we have D, which means that, and both A is also less than equal to D, and B is also less than equal to D. We can see from the hash diagram. So D is acting like an upper bound. The same thing goes for C. A is less than equal to C, and B is also less than equal to C. So C is also acting like an upper bound, and also you have that T is also acting like an upper bound, because because of these relations which I have just marked. You have A is less than equal to T, where T is the topmost element, and B is less than equal to T, where again, as I said, T is the topmost element. So this topmost element T is also acting like an upper bound. So there are 3 upper bounds that we have for the set S, which consists of two elements A and B. One is C, the other is D, and the third is T. But although which means actually that the set of all upper bounds of the set S, which is SU, this is a non-empty set because there are three upper bounds. But then this is how the upper bounds are placed. This is your C, this is D, and the top the top upper bound is T. So all the three are upper bounds of A and B. But then out of these three upper bounds, none of them is least, because C and D could have been the possible least upper bounds, but none of them is a least upper bound because none of them is lower than the other. So in fact there is no relation between C and D, they are non-comparable. So even though the set S has upper bounds, even though the set S, the set of all upper bounds of the set S is non-empty, but still the set S doesn't have a least upper bound. So join of A and B, which is the supremum of S, or which is the least upper bound of S, this does not exist. Now coming to this one, the pair of elements E and F, and I take S to be the set consisting of E and F, and SU, if you try to find out what is SU, then in this case SU, these are E and F, and B is acting like an upper bound for E and F because of this relation. E is less than equal to B, and F is also less than equal to B. A is acting like an upper bound for E and F because E is less than equal to A, and F is also less than equal to A. C is also acting like an upper bound for E because E is less than equal to C, and F is also less than equal to C. D is also acting like an upper bound because E is less than equal to D and F is less than equal to D, and T is also acting like an upper bound because of this particular relation that you have. E is less than equal to T, and F is also less than equal to T. So there are so many upper bounds that you have for the set S is equal to EF, so many upper bounds. But then again, despite of having so many upper bounds, which means that the set of upper bounds of S is non-empty, there is no least upper bound of the set S, there is no join of E and F. Why? Because again, out of these upper bounds, none of them is least. These are all the upper bounds, and the upper bounds are placed like this. This is A, this is B, this is C, this is D, this is T, and this is the placement. And we can see that none of these upper bounds is the least. In fact, A and B could have been the possible least upper bounds, but then there is no relation between A and B. A and B are non-comparable. So again, the supremum of S, or the E join F, because S consists of two elements E and F, the supremum of S or the join of E and F, this does not exist. And if we try to find out the supremum of the whole P of set P, that is the join of the P or supremum of P, then supremum of P is that or join of P is that it should be that element X belonging to P such that every element of P is lesser than that. And we can see that T is the topmost element, this which is the topmost element. T is behaving in such a way that every element of P is lesser than this topmost element T, because every element of P is smaller than T, every element of P is lower than T, so every element of P is smaller than T. So in that sense, T is an upper bound, and also it is the least upper bound because this is the only upper bound. From the hash diagram we can see that this is the only upper bound which P has. So this is the only element in P, the topmost element, this is the only element in P such that all the elements of the PO set P are lesser than that. So the topmost element is the join of P. So that was the third example. And now coming to the fourth example. The fourth example is that of power set of X. if we take X to be the set consisting of 3 elements 1, 2, 3, and if we take power set of X, which is the set of all subsets of X, then we already know that the power set of X with respect to the inclusion relation, that is the relation is subset of or is contained in, we know that it's a PO set. And the elements in the power set of X, because X is having 3 elements, so the power set of X, because X has 3 elements, so power set of X has 2 to the power 3 elements, which is 8 elements, and these are the 8 elements which are listed. This PO set has been considered many times in my earlier videos, so we discuss it with every concept. So I discuss it with this particular concept also, and this is how the hash diagram of the power set of X looks, which we have also discussed when we were discussing hash diagrams in the earlier videos. So here X is at the top, the whole set X is at the top, and the empty set is at the bottom. And if we try to find out what is the join of this singleton 1 and singleton 2, then this is singleton 1, this is singleton 2, and the join of these two means what is the least upper bound of 1 and 2. So we can just see that the element which is just at the top of 1 and 2 both, which is this one, this is an upper bound, and this also happens to be the least upper bound, because X is also another upper bound that we have for 1 and 2, but out of this 1, 2, and out of this X, the one which is lower or one which is least is 1, 2. So the join of 1 and 2, singleton 1 and singleton 2, is 1, 2. Similarly, for that, although singleton 1 and singleton 2, this set, if you consider this the set consisting of these two elements, and if you try to find out the set of upper bounds, then there are two upper bounds that this set has. One is 1, 2. 1, 2 is acting like an upper bound, and the other is X. Both of them are upper bounds, but then out of these two upper bounds, 1, 2 is lesser than X. It is the least, so this is the least upper bound. The same thing, if I try to find out upper bound of singleton 1 and let's say 2, 3, then the upper bound of single 3 is going to be that element where they first meet, the common point where they first meet, and that is nothing but capital X. So capital X, this is this capital X, which is the whole set, the underlying set X, whose subsets are being taken, that is the only upper bound of 1 and 2, 3. There is no other upper bound that we have for 1 and 2, 3, because there is no other element which can act as an upper bound. So this X, which is the underlying set, is the only upper bound, and it is the least upper bound of these two elements. So join of singleton 1 and singleton 2 is 1, 2, and the join of singleton 1 and set 2, 3 is X. So likewise, we can pick up any pair of elements from the power set of X, and we can try to find out their join. Again, if we try to find out the join of P, that is the join of the whole set, so that element of P, which is the power set of X, which is such that every element of P is lesser than that, this is capital X. So every element of the power set of P is lesser than the underlying set X, because every element of P is lesser than X. So if you pick up any A belonging to power set of X, then A will be less than equal to X. Less than equal to X means A will be contained in X, because the PO relation in this case is the inclusion relation. So A is contained in X. So this happens for all A belonging to the power set of X. So every A belonging to power set of X is at a lower level than X. So X is an upper bound of the whole set P, and because this is the only upper bound that we have for the whole set P, so this is the least upper bound, or the join of P. So join of P is capital X. And now coming to one last example, if you consider the PO set of the set of reals, the set of real numbers, and less than equal to is the usual less than equal to relation, the usual sense in which we understand less than equal to relation. And if you pick up any pair of elements X and Y belonging to R, which means that if we pick up any real numbers, any two real numbers, then supremum of X and Y, which is the join of X and Y, this will always exist. Because we know that because the set of real numbers is an ordered set, there is an order which is present in the elements. So if you pick up two elements, we know that one is going to be smaller, the other is going to be bigger. So if out of x and y, if this is the case that x is less than equal to y, then y is acting like an upper bound, because y is greater than both x and y. So y is going to be the join. So x and the join of x and y will be y. If y is less than equal to x, if this is the case, then x is that element which is acting like an upper bound for both x and y, because x is greater than both x and y, greater than equal to x and y, which means that the join of x and y is x. In any case, in whatever the case is, whether x is less than equal to y or y is less than equal to x, in any case x join y will always exist. Either it will be y or it will be x, which means that x join y always exists, or supremum of x and y always exists. And this happens for every pair of elements x and y that we choose from R. So this means that every pair of elements has a join in the PO set of real numbers. Again, but if you take S to be any subset of any subset S of R, it is not necessary that the join of S will always exist. For example, if I pick up the set of integers, or if I pick up the set of naturals, or if I pick up the set of rational numbers, then in that case join of or supremum of S, or least upper bound of S, where S is any of these three sets, the set of integers, naturals and rationals, this will not exist, because you cannot find upper bound. The set of rationals doesn't have an upper bound, which means that if these three sets don't have any upper bound, then the set of all upper bounds in this set in all the three cases, that is SU, this is equal to phi. And if there is no upper bound, we can't talk of the least upper bound, or supremum or least upper bound, or join of S. This cannot exist. So join of S doesn't exist in any of these three cases. So it is not necessary that if you take any subset S of R, join of S will always exist. Again, if we try to find out the join of the real numbers, the set of real numbers, again supremum of R, which is the join of R or least upper bound of R, this also doesn't exist for the same reason, because there does not exist any real number such that all the there doesn't exist any real number x such that all the real numbers are less than equal to x. That is not possible. So because all the real numbers cannot be less than any one particular real number, which means that the set of there can be no real number such that all the real numbers are smaller than it, or all the real numbers are lesser than it, or all the real numbers are below it in the hash diagram, which means that there is no top element. Because there is no top element in the set of real numbers, a top element is always that element such that all the elements of the set are lesser than that. So there is no top element in R, or there is no such real number x in R such that all the real numbers are less than equal to x. So for that reason, there is no upper bound of the set of real numbers, which means Ru, which is the set of all upper bounds of the set of real numbers, is phi. And if there is no upper bound of the set of real numbers, then definitely the least upper bound of R, or the supremum of R, or the join of R, this cannot exist. We cannot talk of supremum of R, or least upper bound of R, or join of R. So that was all about the supremum or least upper bound of a subset S, or join of a subset S of a PO set